Okay, so in this one, I want to talk about phase portraits. These are sort of pictures of the long-term behavior of solutions to autonomous first-order equations. Later on, we'll talk about phase portraits for higher dimensional systems where we have more than one dependent variable, where we don't just have a single equation like x prime equals some stuff. We'll also have a second equation, y prime equals to some stuff, and we have to solve both simultaneously. But for now, we're going to content ourselves with this relatively simple one-dimensional situation. And what we're going to do is draw a picture which represents the long-term behavior of solutions to, again, our autonomous differential equation. And this is sometimes very valuable to have because sometimes you don't care about the particular solution to a differential equation as much as you care about the long-term behavior of those solutions. So a phase portrait gives you a really easy way, a really easy access point, a really easy image that allows you to figure out what the long-term behavior is. Okay, let me remind you of a fact from Calculus 1, which is, or single variable calculus, which you might find very useful for this discussion. Recall that if dx dt is positive, then x of t is increasing. I'm not going to belabor this. I'm just going to state this. And similarly, if dx dt is negative, then x of t is decreasing. Okay. In other words, the sign, the SIGN of the derivative is tied to the monotonicity, that is the increasingness or decreasingness of x. Okay. Important idea. You learned about it in your single variable calculus class, I hope. But we're going to use that here. How? Why? What? Well, here's the idea. We're going to draw what are called phase portraits. And again, this gives us, what they do is it gives us a visualization. That's not how you spell that word. Visualization of the long-term behavior of solutions. And this is particular to autonomous differential equations. Okay, so things of the form I'm talking about now. X prime equals f of x, right? Or dx dt equals f of x. Okay, how? How does a phase portrait work? Rather than me trying to sort of say it out loud, I think maybe the best way to think about it is via an example. So let's do an example here. Let's take as our example x prime equals, how about, I don't know, negative 4 times x minus 3. Then clearly what's playing the role of f of x here in this autonomous differential equation is negative 4 times x minus 3. Okay? And one observation that you can very quickly make, which should be obvious, I hope, at this point, is that the equilibrium solution of this differential equation is x equal to 3. And the point is that if you are an equilibrium solution, right? If you are at x equal to 3 at some time, then you're going to be forever equal to x equal to 3. But what happens if you are a little bit off of x equal to 3, either a little bit above or a little bit below? What happens to you? What is your fate? Well, for a stable equilibrium, you converge back to x equal to 3. But if you're an unstable equilibrium, then maybe you diverge away, perhaps to a new equilibrium. Well, there's no other equilibrium here, but in other situations you might, or you might go to positive infinity, or you might go to negative infinity. Yeah. And what a phase portrait will do for us is characterize all of this simultaneously. So in our phase portrait, what we're going to do is we're going to draw a vertical line. I'll draw it like this, and we'll label the equilibrium solution. So we have the equilibrium here. It'll be labeled x equal to 3. And again, if you're ever equal to 3, if you are x and you're ever equal to 3 for any time t, then you're always equal to 3 for all time t. What if you are bigger than 3, though? Let's say if you are bigger than 3, what happens? Well, think about what happens to f of x. So if x is bigger than 3, look here. This part here is negative. It's negative 4 times, well, if x is bigger than 3, then this is positive. So f of x is going to be a negative thing times a positive thing. I hope you understand my shorthand here. It's a negative times a positive, which is negative. Is that clear? It's a negative times a positive, which is negative. Bottom line, it's negative. If you don't like my little circles with pluses and minuses around it, that's fine. Okay, which means or which one? Which means that, of course, x prime is negative, and so if x prime is negative, then x is decreasing. And we represent this state of affairs by drawing an arrowhead, which is pointing down. And this arrowhead, notice, is above, is when x is greater than 3. So I'm drawing this arrowhead like this. Downward, pointing toward x equal to 3. And it's above x equal to 3. Cool. And what about if x is greater than 3? Then f of x is, well, it's still negative times now, but now times another negative. You feel it? If x is less than 3, then this quantity here is negative. And so, and we know a negative times a negative is a positive. And so, x of t is increasing. And I'm going to represent this state of affairs like this, pointing up. And this is the phase portrait. We call this thing here the phase diagram, phase portrait. Phase portrait of the differential equation. Ugh, I don't like the way this looks. Sorry. So I'm just going to pretend it never existed. Okay, great. And okay, so what can we say about this equilibrium solution x equals 3? We see that x equals 3 is a stable equilibrium. It's stable because if we perturb off of x equal to 3 a little bit, either above, if we perturb above, then we're up here somewhere, this downward arrow is going to push us back toward x equal to 3. And if we're a little bit below x equal to 3, then we're going to get pushed back up. So it's more like we're at the bottom of we're a marble at the bottom of a valley than we are a marble at the peak of a summit. We're a stable equilibrium, not an unstable one. Okay? And let's see what happens if we look at, for example, this equation. X prime equals 0.1 x times 5 minus x. Now we have two equilibria. We have x equal to 0 and x equal to 5. So we're going to denote this with a pair of labeled places. X equal to 5, let's pretend is up here. And x equal to 0, let's pretend is down there. Okay. What's happening in between is the question. So if x is greater than 5, then f of x. So of course, just to be clear, this is my f of x now. What can we say about f of x now if x is greater than 5? Well, just think through the signs here. And if you like my, well, I like it. So, you know, I actually don't give a fuck. That's positive. This is also positive if x is greater than 5. And this one is negative. Ouch. And so the result, the product of these three things is going to be positive, positive, negative. I think that's negative. What do you think? So x equal to 5, if we're above x equal to 5, we are pointing downward. We're a decreasing function. If x is between 0 and 5, then what can we say about f of x? Well, again, where 0.1 is positive, x is positive, and 5 minus x now is positive. Look, 3 communion wafers right in a row. And we're, again, equal to positive. So in other words, we're increasing now. So I should draw an upward arrow here. Feel it? And finally, the last case is if x is negative. X negative. Then f of x, it looks like positive, negative. And let's see, if x is negative, then that's positive, right? Which is negative. So we're decreasing, so we draw a down arrow. Wherever f of x is negative, we draw a down arrow, and wherever f of x is positive, we draw an up arrow in our phase portrait. Here is the phase portrait for this differential equation. And now what do you see with your eyeballs? Can you sense it? What can we say about x equal to 5? This one is a stable equilibrium. If we push off in either direction a little bit from x equal to 5, then we will return as time moves forward to x equal to 5. On the other hand, look at x equal to 0. X equal to 0 is an unstable equilibrium. If we push off in the positive direction from x equal to 0, then we will flow toward the positive, the other equilibrium, x equal to 5. Whereas if we push a little bit below x equal to 0, we will go to negative hell, negative infinity. Yeah? Okay. There we go. That's phase portraits, okay? And that will enable you to get a quick picture of the long-term behavior of solutions to first-order autonomous differential equations. Later in life, we're going to learn about systems of these first-order equations, and that's going to, and we will develop a tool called phase portraits there as well. But there, it's no longer going to be just in one dimension. It's going to be a two-dimensional picture. Okay, so long.